In this section, we are going to explore exactly when linear transformations have inverses. So remember, if T is a linear transformation from a vector space V to a vector space W, then S from W to V, notice we swap these, right, is going to be the inverse of T if S composed T is equal to the identity transformation on vector V, so that if we apply transformation T and then apply transformation S, S just undoes transformation T. We just end up where we started. We end up with the identity transformation. And similarly, if we swap the order of the transformation, T composed with S, that'd be the identity transformation on W. So if we plug some vector W into S, S applies the transformation, but then since T is the inverse transformation of S, it undoes what S did and takes us back to where we started. So it just leaves the input unchanged. So if both these things are true, then S and T are inverse transformations. In real life, we have all sorts of situations where we have actions that are invertible, right? If I walk forward 10 steps, I could undo that by walking backwards 10 steps. If I turn my pencil 45 degrees clockwise, I could undo it by turning my pencil 45 degrees counterclockwise. But then there's also operations that don't have an inverse. For example, if I scramble up an egg, there's no way for me to unscramble the egg. I cannot undo it. I cannot inverse the operation. So we're going to explore exactly when inverses are possible. And it turns out that inverses for linear transformations are going to exist exactly the same time as inverses for all kinds of functions exist. So we are going to begin by just looking at functions generally, not focusing on linear transformations. Okay, so let's take a look at a very simple example here. So I have two sets. I have set A, which is just the set of numbers 1 through 5, and I have set B, which is numbers 6 through 10. Now, function f maps set A into set B according to this table. Okay, this is the rule. We want to determine if f is an invertible function. All right. So first, let's just make sure we understand the notation. The input is elements from A. The output are elements from B. And what this table is telling us is that, for example, this row here, we have f of the x value, the 1, gives me 7. Okay, so this is the input from A, this is the output from B. And each row gives me a different input and output. Okay, so let's see if we can construct F inverse. Now, F inverse should reverse the operation. Okay, because F maps A to B, F inverse, the inverse function, should map B to A. So the values that would go here are the input values, which for F inverse is going to be the values in set B. So I'll have 6, 7, 8, 9, and 10. So let's see if we can successfully construct this inverse function. So let's just go line by line. Okay, so looking at this, we know that when we plug in 1 to F, we get 7 out as the output. So if we're inverting this, instead of going this way, we're going to go this way. So if we plug 7 into F inverse, we should get 1 out. Okay, so if we plug 7 in, we should get 1 out. Right? Next one. If we plug 2 into function f, we're going to get 10 out. So if we're going to reverse that, if f inverse exists, then if we plug 10 into f inverse, we're going to get the value of 2 out. So 10, if I plug 10 into f inverse, I'm going to get 2 out. And I could do this line by line. If I plug 3 into f, I get 9 out for the function value. So if I invert it and I plug 9 into the f inverse, I'm going to get 3 out. So if I plug in 9, I'm going to get 3. And it's just the reverse of this. Okay, and the next one, if I plug 4 into function f, I'll get 7 out. So if f inverse exists, when I plug 7 in, I should get 4 out. So let's go back to 7, and then, well, wait a second. I've already got a value for 7 here. What's going on here? The original function, if I plug in 1, I get 7, but also if I plug in 4, I get 7. Now, here's the problem. A function cannot output 2 different values. If I plug 7 into f inverse, if f inverse is actually a function, it cannot spit out both 1 and also 4. It can only spit one of them out. And that doesn't match with what we have here. It would need to be able to spit out 2 values. Okay? We cannot have 2 different inputs to function f mapped to the same value in the codomain for f, because that would mean that I cannot invert it. Okay, if 1 maps to 7 and 4 maps to 7, I can't have 7 map both to 1 and to 4 in the inverse function. It's just not possible. You could only map to 1 value. Okay, what this means is that f inverse does not exist for this function. F is not invertible. This is impossible. Okay? So what we've learned here is that there are certain conditions that we need to meet in order for an inverse function to exist. This particular condition we are going to call one-to-one. A function f from some input set x to some output set y, some codomain y, is called one-to-one if f of x1 equals f of x2 is true if and only if x1 and x2 are the same. Okay? It's kind of a weird way to phrase it, but it means for every output value matches exactly one input value. And that principle is violated here. We have the same output value, but it corresponds to 2 different input values for function f. And so the function is not one-to-one. If the function is not one-to-one, then it cannot be invertible. Okay? So that's the first thing we can check. Do the same input values map, or I'm sorry, do 2 different input values map to the same output value? If so, function is not one-to-one. If not, if every input value maps to a unique output value, then the function would be one-to-one. All right? So because this function is not one-to-one, f is not invertible. All right, let's take a look at another example. Let C map 1 be the set 1, 2, 3, 4, 5, and let D be the set consisting of 6, 7, 8, 9, 10, and 11. We're going to define function G as a function with domain C that maps into codomain D by this table again. And we want to determine if G is an invertible function. So the very first thing we're going to check is g a one-to-one function? We saw in the last example, if we want our function to be invertible, it must be a one-to-one function. Okay? So what I'm looking for is, do I have any duplicate output values here? That is, do I have any two different input values that map to the same output value? So 1 maps to 11, 2 maps to 8, 3 maps to 9, 4 maps to 6, 5 maps to 10. Notice all these values are unique, right? I'd never get a duplicate. And so this function is one-to-one. For each one output value, there is only one input value that corresponds to it. Okay? Okay, well, it's one-to-one, so maybe this one will be invertible. So again, let's try to construct the inverse function and see how far we get. Okay, so for G inverse, since G maps C into D, G inverse is going to map D into C. So the values I can plug in for G inverse are these guys right here. Okay, if G inverse indeed exists. So 6, 7, 8, 9, 10, and 11. So now let's figure out what G inverse is going to look like. Okay, so let's look at 6 first. So I want to find 6 in the output here. Here it is. Okay, so since G of 4 equals 6, G inverse of 6 is going to equal 4. Okay, so G inverse of 6 equals 4. I'm going to do this for each value. 7. And, well, wait a second. There's no 7 here, right? I could do 8. Since G of 2 is 8, G inverse of 8 is 2. I could do 9. Since G of 3 is 9, G inverse of 9 is 3. I could do 10. G of 5 is 10, so G inverse of 10 is 5. And I could do 11. G of 1 is 11, but G inverse of 11 is 1. But there's no 7 in the image of function G. Nothing maps to 7 in the codomain. There's nothing there, okay? Which means G inverse doesn't make sense as a function. For a function to be a function, I need to be able to map everything from the domain into the codomain. And here we do not have a rule for what to do with 7. Okay? Because 7 does not appear in the image of G, in the range of G. Okay? So we've encountered another problem. This means that G inverse does not exist. The problem this time is that we're one-to-one, but there are values in the codomain that the domain does not map onto, specifically 7. 7 is never mapped onto. Okay, so this is going to be the second criterion that we need to have a function be an inverse. Okay, to be invertible. A function f from x to y is called, we call this property being onto. We say it is an onto function, as in x maps onto y, as opposed to into. Into y is just any old function. Okay, G maps C into D, but if I were to say G maps C onto D, that means every value in D is mapped onto. Okay, so function f is called onto if for every, let's say each actually, for each value y in codomain y, there is some value x in domain x so that f of x equals y. Okay? Math speak for saying we're going to reach every value in the codomain. Everything gets mapped onto. Okay? And that's not what's happening here, because the 7 does not get mapped onto. Everything else does, but the 7 doesn't. So this is not an onto function. All right? So we have two criteria now. In order for a function to be invertible, we know it needs to be one-to-one, and we know it needs to be onto. All right, let's look at one more example here. Let's let set A be the set of numbers 1 through 5. Let's let set B be the set of numbers 6 through 10. We're going to define a function h that maps A into B as defined by this table. So is h an invertible function? Well, we know we need to check two properties. Is it one-to-one? And is it onto? All right? So one-to-one. One-to-one means that each value in the codomain is mapped to only once. All right? There are no duplicates. There are no two values from the domain that can map to the same value in the codomain. There's one value in the codomain for each one value in the domain, one-to-one. So we're really looking for any duplicates here. Are there more than one way to get to a value in the codomain? So I'm looking at the values in the codomain, the output values. I'm not seeing any duplicates, 9, 6, 7, 10, 8. Because there are no duplicates, that means the function is one-to-one. Okay, there's only one value that we could plug in here to get each of the output values. Okay, now let's check if it is an onto function. For an onto function, we better be able to map to each one of the values in the codomain. Let's check them one at a time. Do I map to 6? Well, yes, I do. 2 maps to 6. H of 2 is equal to 6. What about 7? Yeah, H of 3 equals 7. 8. H of 5 equals 8. 9. Oh, H of 1 equals 9. And 10. H of 4 equals 10. So, hey, that was all of the values in my codomain, which means the function is onto it. Maps each function from the domain onto the values in the codomain. We reach each value in the codomain. We don't leave any out. So is this finally enough? Do we have an invertible function? Well, let's see. Okay. H inverse, since H maps A to B, H inverse is going to go the opposite way. It's going to map B into A. So B has elements 6, 7, 8, 9, 10. So that'll go over here on my right-hand side for my table that's mapping H inverse, if it exists. And then we just check for each value here. So we want to know if I plug 6 into H inverse, what will I get? So we'll just undo H. So since H of 2 is 6, H inverse of 6 is 2. So H inverse of 6 is 2. 7. H of 3 is 7, which means H inverse of 7 is 3. 8. Since H of 5 is 8, H inverse of 8 is 5. And I could keep on going. 9. 9 corresponds to 1. And 10 matches up with 4 here. Okay, and look at that. We have actually a complete inverse function, which means function h is invertible. Okay, and here's the inverse. So what we've just learned is that there are two conditions that we need to meet in order for a function to be invertible. The first, the function must be one-to-one, and the second is the function must be onto. Okay, so a function f from some domain x to some codomain y has an inverse function if and only if f is 1-to-1 and onto. If it meets both those criteria, then guaranteed f will have an inverse function. If either one of these fails, if it is not 1-to-1 or if it is not onto, then f will not have an inverse function. Now, we're talking here about general functions, but remember linear transformations are a special kind of function. They are a function from a vector space to a vector space that have some additional properties that make it linear. But at its root, it's still a function. So it will be invertible if and only if it is 1-to-1 and onto. A linear transformation will have an inverse transformation if and only if it is both 1-to-1 and onto.